was it the kinematics joke? Okay, here are the steps to calculating torque. Here we go. It's a lot of steps. Okay, let's calculate a torque. Clearly we need that to be able to think about circular motion. Step one, I bet you can guess what step one is. ID and axis of rotation. Does it need to be the axis the object is actually going to rotate about in your reference frame? Technically, no. But if you want the problem to make any sense, then yes. So figure out what axis you're rotating around. Okay? Step two. We're going to do this for something I won't even think about setting up at this point. Is this disc has some radius, it has some mass, and we can tie a string around it and just hang a weight off the string like that. And the disc is pinned here, it's got a bearing there, and this has mass M. So you can imagine what happens is the weight pulls it down and makes it spin. Okay, so that's the torque we're going to start out thinking about. So step two is draw R from the axis to the point forces applied. Draw R, that's the R vector I was talking about up there. From axis to the point, the force is applied. So we say, okay, the axis of this rotation is like this. Where is the force being applied to the disc? You've got to think about that a little bit. You might say the force is being applied here. That's when the force is being applied to the mass. But we know that results in tension here, and the tension applies a force to the disc. And if you don't know, I'm going to tell you, a string wrapped around a disc applies a force to it at the point it leaves the disc and in the direction of the string. So the force is being applied here, like that. So that is what I want to call it. I'm just going to call it. Oh, it's not equal to mg because it's falling. Crap. I'm going to call it F. Great creators. Thank you. So we got a force down. And now you can see, suddenly, it's important that this is not a first order. Because we have to draw a vector, R, from the axis to the point the force is applied. It's like the force is being applied at a specific place on the object. And that's because we're doing rigid bodies now that have a size. So that's why we can't just say, oh, let's look at that. We have to actually think about where the force is being applied. Step three is draw the force. So I did that. So right now it's just a little, tension force from the string. Okay, so I drew the force in the right place, where it goes, like that. That was wonderful. And then 4 is find the angle. That's not the angel. The angle theta between R and F, like that. And in parentheses, I'll put tail to tail. When you add vectors, you add them head to tail. But when you're asking for the angle between two vectors, you do it tail to tail. And I'm going to give you just drama of how to do that. We're sorry, think about that. Okay, we're calculating torque. We're trying to figure out how to calculate torque. We said, okay, what was it? Find the axis of rotation, draw the R vector, draw the force vector, find the angle between R and F, add them tail to tail. So what I would do now is draw them off of the drawing. Okay, so on the drawing, they're never tail to tail. Almost. No, never. They're going to work. So you got to draw them off, and you say, okay, here is R, and tail to tail, there's F. I would draw them like that. Yeah, let's see. The first question on the pill thing. Oh, wait. So why isn't Nick? Yeah, some kinetic friction for this question. Let's not worry about it. Those are all just for fun. We'll worry about it later. Okay, so I'm going to draw them, and I'm going to realize theta. So now we get into, do you want to use RF sine theta, or do you want to use RF perpendicular? Okay, so RF sine theta is sort of the technical way to do it. RF sine theta. And if you define that theta correctly, you'll get a number with a negative sign that you can use. Okay? These are magnitudes. The R means the magnitude of the R vector. The The F means the magnitude of the F vector, and this is what I'll call a proper theta. Okay? Don't look that up on Urban Dictionary, I don't know what it means. But I'm calling it a proper theta. So the proper theta here, so what is the magnitude of R vector? It's not just R, what is the magnitude? It's big R. So typically you'll plug in something from your problem there. The length of a rod, half the length of a rod, the radius of something, the number, if they gave you the number. F, you'd probably get an F for the problem. In my notes, I was silly and put mg, but it's not mg because the thing is accelerating. Oops. Sorry. So we're just going to say it's F. Well, we can say it's T. It is the tension. There you go. The force would be the tension in the string, which would not be mg. It'd be lower because it's accelerating. So RT, and then what is this theta? Due to the problem, it's 90 degrees. Right? So the string will separate from the pulley right at this point based on the geometry of a if the line is tangent right there, it'll be 90 degrees. This will be straight down, this will be straight over. Most things will be based on more solid geometry than that. But you just have to believe me, this is 90 degrees. But it's negative 90 degrees. Okay? The order actually matters. R to F. You go from R and you go to F, and if I go from R to F, I'm going clockwise. And clockwise is negative. This is theta equals 0, this is theta equals negative 90. So sine of negative 90. So what we find is the torque is minus RT sine theta, or sine of negative 90 is negative 1. Right? So it's minus R times T is the torque. You could also do it, though, with this other way, this, where did I write it? Up here, RF perpendicular. So you can also, in this way, I don't know mathematically what it really means. So RF sine theta or RF perpendicular. I mean, it really means the same thing. We're not doing anything different. This R, this is the magnitude. The R is the magnitude. This is the F component perpendicular to R vector. That's what those two symbols are. So basically, when you find the component, you're just doing F sine theta in one step. Sometimes when you look at a problem, it's easier to see that. Okay. What is the second T? This is a tension. I just said, oh, well, the force is really the tension. I was going to call it F, I was supposed to call it T. Yeah, sorry. So that's the tension. Let's see. So we say, okay, the magnitude of R, the R vector, is big R. Right? That's the radius that you were given in the problem. Force perpendicular is you just look at the problem and say, can I calculate the component of this force vector perpendicular to this vector? Well, in this case, yeah, it's all perpendicular to that vector. And there's no trig to do, right? It's just F, or it's just T. You don't even have to think about the sine theta because you know it's at 90 degrees in that direction. You could say, okay, then that's easier, right? And just say, oh, well, it's just T, right? Because it's all perpendicular in this case. We'll do cases where it's not all perpendicular, but in this case, it's all perpendicular. But if you do it this way, you may not get the sign right. The sign isn't done for you. Okay? If you do it this way and make your sign magnet, your sign thing proper, the sign will be right. If you do it this way, you kind of have to give it the sign yourself. So we've got to remember, what does the sign mean? So here I know that it's going to be negative. And the way you know is the sign, the torque, sine goes, oh crud, I didn't write this ahead of time, with, can spell, the direction it pushes. That's not bad from the top of my head. Oh, it's pretty bad. The torque sine, I would say, is the direction that it pushes. So, which way is this thing going to turn if it's free to turn under the torque? It's going to turn clockwise. Clockwise is the negative direction. That's why when we put in the sign negative theta, negative 90, we got a negative sign. So this negative sign means, because these are magnitudes, these are positive, this negative sign means this torque is making it turn clockwise. And when you calculate RT here, if you do it this way, you have to say at the end, okay, now, which way is the torque going to make it turn? It's going to make it turn clockwise, so I better add a negative. one way or another, the negative has to come out, because the negative tells you which way it's going to turn. It's really a vector. We're going to talk about that. Let's see.